continuing our review. This is, by the way, the last day of the semester. I know you are excited about that, although you're probably sad that you're not going to get any more physics for a while. Nor chemistry, nor astronomy, nor geology. So let's pick up with thermodynamics, try to whip through the rest of this physics, get through some chemistry and geology. So thermodynamics is specifically looking at energy transfers, and heat is one of the two ways we have energy transfer. Heat is energy transfer without doing work, and work, of course, is energy transfer with work. And so heat, the symbol for heat is Q, and we have a number of rules to deal with this. So first thing is we had to define what temperature was. And the somewhat shocking realization that temperature is more than just, hey, it feels hot or it feels cold. It's not something that's based on how it feels. It's based on the actual average kinetic energy of the molecules. So the temperature, now the relationship between average kinetic energy and temperature is different for different materials. But it's telling you about the average kinetic energy of the molecules. Higher temperature, they have higher kinetic energy, means they're going faster. And so when molecules hit you, they either deposit energy on you, in which case you feel warmer, or they will pick up energy from you, bounce off with a higher energy, and you feel cooler. Then we had 4 laws, the 0, 1, 2, 3 laws of thermodynamics. And so you need to know these laws. The 0th law is that if temperature 1 equals temperature 2 and temperature 2 equals temperature 3, then temperature 1 equals temperature 3. It's a very simple law, so simple that nobody would have ever thought you had to define that law. But when they understood that temperature was a little more complicated, then it wasn't as obvious, and they decided they had to make this law. The first law, energy can't be created or destroyed. It doesn't mean you can't convert energy. But when we talk about power generation and our energy resources, it's not that we are getting energy from this thing. We're converting energy it already had into energy we can use. It's not creating it. It's just converting it to something we can use. And so in equation form, we can write this first law as the white pen doesn't work out very well. The change in internal energy, we usually use U for that internal energy, is equal to the heat added minus the work done by system. It's important to pay attention to the direction. The reason there's a minus sign there is because heat added is energy coming in, and work done by the system is energy going out. Hence, the change in internal energy is what you put in minus what you take out. That's why the signs are the way they are. You can think of it like your bank account. The change in balance is equal to the deposits from your paycheck minus the expenses from your checkbook. The second law, heat naturally flows from hotter things to colder things. That's one of the statements. That's the only one that we worried about. Heat naturally flows from hot to cold things. So if I bring two things in thermal contact, like an ice cube and my skin, heat naturally flows from the higher temperature item. Which one's higher temperature, generally speaking? My skin or the ice cube? My skin. Unless you talk to my wife, who will say it's the ice cube. So my skin is warmer, hence heat flows from my skin into that ice cube. What happens to my hand when the heat flows out of it? It feels colder. What happens to the ice cube when heat flows into it? It melts. Generally, that ice cube is going to be at its melting temperature, so when heat goes in, instead of changing the temperature, it changes the phase, and it stays at constant 0 Celsius. Once it melts, if I have water at 0 Celsius, that's still colder than my skin. Heat's still going to flow from my skin into the water. Then what's going to happen to the water? Once it's melted and heat goes into it, what does it do? It's going to warm up. The temperature's going to rise then. And so we had this calorimetry thing that said the heat that's flowing into something that's not changing phase, not melting, not freezing, not boiling, not subliming, is the mass of the material times the specific heat that's different for different materials multiplied by the change in temperature. So you have to know what the specific heat is to work with that problem. You have to know what the mass is to work with that problem. What are the units of heat, by the way? Okay, joules is a correct answer. That's the standard unit, so it's the most correct answer. But oftentimes we'll use a different unit, the calorie. So a calorie is also a unit of energy, but it's specifically used as a unit for heat. So 1 calorie is the amount of heat required to raise 1 gram of water by 1 degree Celsius. So it has a specific definition there for what a calorie is. Now, if you're on a diet and you count calories, how many people can tell I've been on a diet? It's been almost a year now, and I've only lost 70 pounds. It's 70? Yeah, it's rather distressing.
Wait, 70?
Yeah.
That's a lot.
That makes it my, third best diet. And my other diets, I lost it so much faster. But anyway, when you count your calories, what are you counting? Calories are units of energy. You're counting the energy that you are eating. But the dietary calorie is 1,000 of these calories. So 1 dietary calorie is equal to 1,000 calories. And we write the dietary calorie as CAL with a capital C and the normal calorie with a lower c. So it can be confusing. Now, I don't want to confuse you, but you certainly could have a question to ask about the relationship between the dietary calorie and the calorie defines the amount of heat required to raise 1 gram of water by 1 degree Celsius.
Is that just one of the 1,000 calories of the dietary?
The dietary calorie is 1,000 regular calories. So most people only know about dietary calories and don't realize it's based on another unit. And so technically, this is equal to 1 kilocalorie. So dietary calorie is a kilocalorie. And I suppose people didn't want to say kcals, which, by the way, is the name of a radio station I used to love when I was in college. Okay, thermal expansion. When things are heated up, they usually expand. Why? It's easy to explain. You have molecules that are moving in a solid or in a liquid or even in a gas. And those molecules bounce off of each other. And if they're higher temperature, they're going faster, they're hitting each other harder. And so they spread out because of the harder collisions. And so that makes things expand when you heat up. It's a very natural process. There are a few things that don't do this. It's really important to know what's the common thing that shrinks when you heat it. There is plastic that does that, but it's not the common thing. I mean, shrink wrap, obviously. Water. Water at room temperature, it will actually contract when you heat it and expand when you cool it. Is that right? No. It's water below 4 degrees Celsius. Above 4 degrees Celsius, it's normal. But below 4 degrees Celsius, down to some really cold temperatures, it works backward. So 4 degrees Celsius, it is the least dense. And if you cool it or heat it for 4 degrees Celsius, it will become, I said it backward again. It's the most dense. If you heat or cool, it becomes less dense. So that when you freeze water, it expands, hence cracking pipes. Can't believe I butchered that one.
Wait, if you heat or cool it, it's less dense?
from 4 degrees Celsius.
Oh, okay. Wait, but then if it's 4 degrees Celsius and it goes up to 5, or anything below that?
Either way, it will expand. So if you heat water at 4 degrees Celsius, it expands. If you cool water at 4 degrees Celsius, it expands.
Oh.
And of course, if it's at 5 degrees, if you heat it, it expands. If you cool it, it contracts until you get to 4. So that's important. It's important because if it didn't happen, ice wouldn't float. And if ice didn't float, then we would have lakes freezing solid, and frozen solid lakes would, well, first of all, be bad for fish. And second of all, it would result in more energy being lost by the water overall, and thus it would overall have a cooling effect on the earth. One more thing on this. What was that one more? Oh, yes. Water has a very high comparative specific heat. That's another important thing. Remember, the earth is roughly 2/3, a little bit more than 2/3 covered with water. Water has a high specific heat, which means that if you add a lot of heat, the temperature doesn't change much, right? Because if Q is large, and then you divide by MC, and C is large, delta T is going to be smaller with a large C than it would have been with a small c. So temperature change isn't as big because you have that large specific heat. So if you're from California, as I am, you have a big ocean there, and that ocean is going to keep the temperatures from having big fluctuations. So California in the wintertime at this latitude is much warmer than Lincoln, Nebraska at this latitude, unless you come inland and go up in the mountains. You come inland and go up in the mountains, of course, then it gets cooler, but you're farther away from the water, and that's why, and higher elevation. So that water is what makes people have the image of the beach in California and such, lovely weather in the winter. 3 methods of heating. Conduction, direct contact. Convection is an intermediary, like water or air. We just purchased a convection oven. The convection oven, basically it has a box in here and there's no burner. Off to the side, there's a hole. And in here you have your burner that makes hot air. And then you have a fan that blows air through that and out the hole. And so you're blowing hot air into the oven to cook with. It's convection, it's forced convection in this case because the fan is forcing the hot air to go where you want it to go. But that's what convection is. So if you look at a convection oven, the convection oven is heating air and blowing the hot air on your food, rather than having the heating element out there where you can put your hand in there and touch it. Radiation is through electromagnetic waves. Light is an example of electromagnetic waves. So heating through radiation could be heating through light. And you all notice that. If you go out in a sunny day, I've got sunshine. It's nice and warm because you have heat coming from the sun. And even in the middle of the winter, if you have a sunroom with nice windows so the sunlight can come in, it might be 20 below outside, but that sunlight, you stand in the sunlight and you feel the warmth coming from the sun because that's radiation bringing energy, bringing heat. So you have those 3 methods. Newton's law of cooling, we won't worry about that, okay? Newton's law of cooling says that the rate of cooling is proportional to the temperature difference. Yeah, you don't need to know that. Okay, so I'll take that off. Do know the greenhouse effect, though. Right? That's something that's really big these days. Is the greenhouse effect real? Yes, it is. Is the greenhouse effect good?
Yes.
Yeah, can be. We talked about this and we had differing opinions, and that's fine. We have to have the greenhouse effect or we freeze. But too much greenhouse effect and we cook. Venus is an example that's cooking because it has too much greenhouse effect. Mars is an example that doesn't have enough greenhouse effect And it's fine if the sun is shining well. On a nice summer day near the equator, the temperature is fine on a sunny day. It's, like 70 degrees Fahrenheit, roughly. But at night, it gets super cold because it doesn't have enough atmosphere to hold the heat in. Know how water is unique and why it's important to sustain life on Earth? It's the two properties I talked about, the large specific heat and the fact that below 4 degrees Celsius, when you cool it, it expands instead of contracting. The things we've talked about. Electricity, we only talked about very briefly. So you need to know you have a force between charges. That force is attractive if the charges are opposite. So we have two types of charges that Ben Franklin randomly chose to say that the thing that was on amber was negative. And it's called an electron because that's the name for amber in Greek. So we have negative charge and we have positive charge. Opposites attract, likes repel. And the force is just like gravitational force. That is, I'm putting a highlighter. It's proportional to the electric charge of one object times the electric charge of the other, divided by the separation. That R means the separation between the centers of the two charges squared. So just like last class period when I talked about the force between Gabby and Ivy versus between Gabby and Ashton, and because Ashton is twice as far away, the force is only 1/4 as strong. With the electric force, it's exactly the same law. If you go that bigger distance, it's going to be a much weaker force. And that's called Coulomb's law. So that's basically it for the electricity. We have to know that because when we get to chemistry, that's really important. So we jump right to chemistry. We skipped over the waves. We didn't get sound. We didn't get light waves.
So that's not going to be in the test.
Right. So with atoms have a nucleus that contains protons and neutrons. And they have electrons going around. Now, with earlier models, they thought that the electrons were like doing circular orbits around the nucleus. Now we know they're not. We don't know what they're doing. We just know they're not necessarily doing circular orbits. We can't tell you what they're doing. But we can calculate where they're likely to be. So that's why it says here the electron cloud. But the electrons have distinct energy. You'll remember that I brought out the lamp. You wore the cool glasses that broke light up into its separate colors, and you could see, hey, there's this color, and there's nothing in between. And that's because your energy levels for the electrons are very specific. You have the energy shells for the electrons, and we have the rules for how many electrons could go in a shell. So in the first shell, just look at the periodic table, how many electrons can go in the first shell? 2, because there's 2 elements in the first period, first line, and that's filling the first shell. Now the second line, the 2 on the left, are filling the first shell again, but in the second energy level. And then the next one, so there's 6 more, are filling the second shell. So there's 6 electrons that you can put, actually a second subshell, I should say. So you have a total of 8 in that second shell, 2 in the first subshell, and 6 in the second subshell. Excuse me? Yeah, 8, because it's 2 plus 6. I'm counting. So we have the periods are the, periods and what do we call the columns? Yeah, groups. Groups. So we have periods is telling you which shell you're filling, essentially. And the columns are telling you about the chemical properties. That's what Mendeleev did when he put together this table. He put materials with the same chemical properties in the same columns. So everything in the first column has very similar chemical properties. We call those alkali metals. Second column has similar properties, actually quite similar to the first column, but a little different. And those are the alkali earth metals. And then the ones that are shifted down, that are labeled back there, 3 through 12, those are the transition metals. Those are the things that you and I usually think of as metals. In astronomy, anybody know what's considered a metal in astronomy? Anything that's not hydrogen or helium is considered a metal in astronomy. They have a different periodic table. You get over to column 13, I don't know the name. 14, no. 15, no. 16, you don't need to know it, but our textbook calls them the chalogen. 17, you need to know. The halogens. Fluorine, chlorine, bromine, iodine. Is it actinide? No, not actinide. I don't know, AT. Those are the halogens. What's special about the halogens?
They're very active.
Okay, they have a very high electronegativity, which is the key she's looking at there. Because they have a high electronegativity, they really want another electron. On the other hand, the alkali metals have a very low electronegativity. They don't really care about their last electron. And so when you get a fluorine and a hydrogen together, the fluorine says, I want that electron. The hydrogen says, yeah. And so the electron goes from the hydrogen to the fluorine. Then the hydrogen is ionized because it's missing an electron. The fluorine is ionized because it has an extra electron. They now have opposite charges. Fluorine is negative, hydrogen is positive. According to Coulomb's law, opposites attract and they form an ionic bond. Another thing about size, I was just grading homework 6. Size is related to how strongly they're holding on to the electrons. So things like the halogens that are holding on to those electrons really tightly are going to be smaller in size than things in the same period that are on the left-hand side that don't care about the electrons as much. So you actually, even though you're adding protons to the nucleus and electrons to the cloud, the size of an atom gets smaller as you go across the periodic table toward the inert gases. The size also gets larger as you go. It gets smaller as you go up, larger as you go down. So basically, bottom left-hand corner, francium, is going to be about your biggest, and top right-hand corner, helium, is going to be about your smallest atom. Atomic number and atomic mass. Very simple terms, easy to get them confused because they're so similar. Atomic mass is telling us about what the mass of the atom is. So that's combining everything. That's how to keep them straight. So the mass is counting the number of protons plus the number of neutrons. Protons and neutrons have very similar mass, so if you just add those up, it gives you a number that's roughly equal to the mass of the entire atom.
It doesn't include the electrons.
It doesn't include the electrons simply because there's not many electrons, or not many electrons, there's not much mass to electron. This is, by the way, projectiles from the railgun. If you're wondering why you see, this is the second one I picked up today. It was very cool. So they don't count the electrons in the atomic mass because their mass is so small compared to the mass of protons and neutrons. So atomic mass is number of protons plus number of neutrons. And the mass of an atom is roughly close to equal to the atomic mass in atomic mass units. The atomic mass unit is the mass of one proton or the mass of one neutron, which are very similar to each other. The atomic number is the number of protons. Why is the atomic number called such a generic term? Because elements are identified by the number of protons. So if it has 7 protons, it's always going to be nitrogen. Doesn't matter how many neutrons. The atomic mass doesn't tell us it's nitrogen. The atomic number tells us. So nitrogen normally has 7 protons, 7 neutrons. What's the atomic mass for nitrogen if it has 7 protons, 7 neutrons? 14. So nitrogen most commonly has an atomic mass of 14. But you can make carbon 14. That also has an atomic mass of 14. It has its carbon. How many protons does carbon have? Mr. Brown, if you don't know.
Oh, proton 6.
6, right. The number in the top right corner. Remember, you're going to have a table like that on the test so you can look at it. Don't have to turn around. So it has an atomic number of 6. If it had 14 nucleons, got atomic mass of 14, then it must have 8 neutrons. So carbon-14 has 8 neutrons, 6 protons. So notice here there's one more thing I didn't mention yet, the noble gases. The noble gases is the last column in the periodic table. They're noble because they stand alone. They don't hang out with anybody. So helium does not form bonds in an unexcited state with other atoms. It just sits there. It's got its valence. Remember, the valence are the outer shell of electrons. Its valence shell is filled. So it's got all the electrons it wants. It doesn't want any more. And so it's inert. So another name for the noble gases is the inert gases, because they just don't participate in chemical bonds. So you generally don't have a molecule with helium in it, or with neon in it, or with argon in it, or with krypton in it. So, and I already talked about transition metals. So you need to know those from the periodic table. Quantum theory is a theory that says that the different parameters, like the energy, angular momentum, a number of other things, for electrons in the atom are quantized. They can only have certain values. So you can only have specific angular momentum. That is, if you think about angular momentum for me, that's going to be the rate at which I'm rotating multiplied by something that has to do with my mass distribution. And so me having only quantized angular momentum would be like I can only rotate at this speed, or I can rotate at this speed. But I can't rotate anywhere in between. That's what quantum physics says about the atom. Pretty bizarre when you think about it, because in real life, there's nothing that says I only have certain speeds I can rotate at. Quantum mechanics says, well, no, really, there are only certain speeds, but the difference in those speeds is so small that you can't tell from my rotation. But for the electrons, you can. So that's what quantum theory means. And how does that relate? Well, using this quantum theory, it tells us that we have only certain energy levels that electrons can have. And when you put electrons in, they're going to go to the lowest available energy level. But when you fill it up, they have to go to higher ones. And that's why we have the different chemical properties. The distinct line spectra, that's going back to when we had the lamp and we saw only specific colors, are caused by electrons falling from one energy state to another. And when they fall from one energy state to another, the difference in energy is given off as a photon, a particle of light, and so the energy of the photon, which is Planck's constant times frequency, is equal to the difference in energy levels of those two states. So going from energy 3 to energy 1 is a bigger change in energy. It's going to produce a photon, a particle of light with higher energy, and that's higher frequency. The smaller jump, lower energy photon. And different frequencies are different colors, hence we see them as distinctly different colors in that spectrum when we're wearing the glasses. Yes, radioactivity. Radioactivity, we talked about, occurs because the nucleus is in a quasi-stable arrangement. It could be more stable. It's kind of like if I have this remote and I could get it, let's suppose I could get it perfectly balanced. I can't, right? I'm not that kind of talent. But if I could get it perfectly balanced here, it would be kind of stable, but any little thing like, me bumping the table would make it fall down to a more stable configuration. That's what radioactivity is. It's going on in the nucleus, though. And with radioactive decays, they found initially 3 types of radiation that they classified by how easy they are to stop. Alpha radiation, really easy to stop. Your skin forms a perfectly effective barrier protecting the rest of your body from alpha radiation. Of course, that means you are absorbing energy in your skin from alpha radiation, which can cause mutations and thus cancer. So protect yourself. Put a piece of paper or sunscreen on. Sunscreen not only protects you from the UV radiation, it's going to absorb the alpha particles before they get through. It doesn't take much to stop an alpha. Betas, it turns out betas are electrons. There's also the beta plus, it's the positrons, like an electron but positive. Those are harder to stop. So if you're going to protect yourself from that, you're going to need something like some lead shielding. And then gammas, which are electromagnetic radiation. They're light waves in essence. They're just very high frequency. That's really hard to stop. You need significant shielding to stop gamma radiation. So if you have something that's radioactive, if it's giving off gamma radiation, you really need to worry about safety. If it's giving off alpha, if you're wearing clothes, you're probably safe, except for the parts that are exposed. Radiation dose, we didn't talk about dose calculation, so let's not worry about that. Radioactive decay, half-life. Half-life is the time for 1/2 of a radioactive sample to decay. So like we had a homework problem that said you go from 80 counts per minute to 5 counts per minute in 8 hours, and it asks what's the half-life. Well, the way to calculate that is the half-life is the time to drop in half. So 1 half-life, you would have 80 divided by 2 is 40 counts per second after 1 half-life. Second half-life, you go from 40 to 40 divided by 2, 20. Third half-life, 20 to 10. Fourth half-life, 10 to 5. So it's gone through 4 half-lives in that problem. And then you're like, well, 8 hours is 4 half-lives, so a half-life must be 2 hours. That was the solution to that problem. So make sure you understand that process of what a half-life means and how to make it applicable. That is what is used in things like radiometric dating. If you know how much material you started with and you know how much you have now, then you can just calculate how many half-lives it's gone through and determine its age. Finally, nuclear fission and fusion. Fission is a nucleus breaking into smaller pieces. Things like uranium can undergo fission and break into 2 smaller pieces, and in the process give off energy. Fusion is 2 small pieces merging together to make a bigger piece. That happens with small pieces, things like hydrogen or helium. Hydrogen and helium can release energy if you make them undergo fusion. It's hard to make them undergo fusion because 2 protons naturally repel each other. Right? You've got that electrostatic force that's trying to push them apart. So they have to be going really fast. What does that translate to in terms of measurables for the molecules or atoms to be going really fast? High
energy.
High energy, which means high temperature. So they have to be high temperature if you're going to make them undergo fusion. You also need high pressure because you have to have a high probability of them actually hitting each other. So that's necessary to make fusion occur. There is much more energy available per mass in fusion than fission. Okay, now getting into straight chemistry. Be able to define what a chemical is. What's a chemical? It's a very basic thing that we normally take for granted, but for a class like this, you're going to go teach grade school kids or high school. It's important to know, what does it mean if it's a chemical? It's made of atoms. How many things are chemicals? Everything, okay? Everything. Chemicals does not equate to bad. It means that it's made of atoms. What's a molecule? It's one unit that is bound together as a unit. So a molecule, you do have monatomic molecules, like helium forms monatomic molecules. It's just one helium atom is the molecule. But more often you have something like H2O. That's 3 atoms, 2 H's and an O. What name do you give to H2O? Water. If you were going to name it scientifically, how would you name it scientifically? dihydrogen monoxide. So you use a prefix for the number, and then the second word, you as a standard, replace its ending with an I. So water dihydrogen monoxide.
So what would the definition for that be?
Excuse me?
What would the definition for that be?
A molecule is one or more atoms that are bound together as a single unit. Okay, elements. Everybody got the element question right in the homework. Elements are just one number of protons in the nucleus. They all are the same type of atom. Compound, more than one type of atom in your molecule. So water is a compound, right? Because it's got H's and it's got O's. And a mixture, remember mixtures, we had homogeneous mixtures, heterogeneous mixtures. Mixtures when you have things that are mixed together. So one kind of molecule, another kind of molecule. And if it's homogeneous, you can't tell that it's two kinds of molecules. If it's heterogeneous, you can. So we had some gross examples like a pizza. You can tell the difference in your mushrooms and your jalapeno peppers, two of my favorite toppings for pizza. So that would be a heterogeneous mixture when you can tell the difference. Homogeneous when you can't. Alloys are very special. Alloys are only something you can make with metals because metals have a unique kind of bond. We will spend a few minutes here talking about the ionic bonds versus the covalent bonds. Metal bonds are a third type of bond that is a bond from the electrons being not localized. Delocalized is the word we use. Electrons are throughout the metal and they hold the atoms together. And you can easily replace one metal atom with another metal atom and it hardly makes any difference. And so alloys are made by mixing different elements that are metals together and getting different properties. So you can make the Sacagawea dollars that look kind of goldish. They don't have any gold in them at all. And I think they're alloy of silver, aren't they? I don't remember what they're alloys of. But that's what an alloy is. Physical properties versus chemical properties. Physical property is that you have the same molecules, but they're in a different form. Chemical changes are when you have a different molecule. And so you had a homework question that asked, is boiling a physical or a chemical change? Answer, it's still water. It's still H2O. So it is a physical change, but not a chemical change. Another one that was tough was a bone healing. A bone healing, you actually have chemical changes. You're forming new molecules as the bone heals. So that's a chemical change. Now, a lot of people said that's a physical change. Chemical changes almost always also have physical changes, but if it has a chemical change, we classify it as chemical. If it doesn't have a chemical change, but it has physical change, then we classify it as physical. Question?
So the one that I never understood is when it asks whether density is a physical property or chemical property. And I think is it physical?
It's physical, yes.
Yeah.
Because you're just making the molecules closer together. You're not changing the molecules.
Oh, so it's just closer together. Okay.
Yes, you're bringing two molecules that are normally separated by this. You're compressing them so they're separated by this. But they're still, each molecule is its own thing. No change. Just like that would be the same as changing from gas to solid. The solid has the molecules much closer, hence a higher density. But it's still the same molecules. And then be able to name simple compounds. Well, I practice that with the H2O. Make sure that you can do that because you'll certainly have to name something on the test. Wow, only 10 minutes left. The electron dot structure. Remember, the electron dot structure is only showing the valence electrons, and it helps us to understand covalent bonds. The electron dot structure is really only used with covalent bonds. So let's talk about covalent bonds. Co is our key word here. Co, if you are cohabitating, what are you doing? You're living together, sharing a habitat. And that's what a covalent bond is you have valence electrons that are being shared by atoms. So you have, for instance, a fluorine. that would really like to have 8 valence electrons, but alas, it only has 7. So its Lewis dot picture for fluorine has 2, 2, 2, and 1 electron. Well, you bring another fluorine by, and each one says, I want another electron. And then they say, hey, why don't we just share? And so each one shares an electron with the other. So each one's like, counting the one you're sharing with me, I have 8. And then they're happy because they have a completed shell. That's what a covalent bond is doing. A covalent bond between 2 fluorine atoms is nonpolar because the electron is going to be shared exactly equally between the two. If, on the other hand, you had a covalent bond between, let's say, fluorine and carbon, the fluorine has a much higher electronegativity than the carbon. So they're not going to share equally. The fluorine's going to say, gimme, gimme, gimme. The carbon's going to say, I want it, but not nearly as badly. So the carbon's going to end up with a slightly positive charge because it's giving more than it's getting. The fluorine will end up with a slightly negative charge because it's getting more electron than it's giving. And so that would make a polar covalent bond. And of course, if the electronegativities are big enough, like the example I gave at the beginning of chemistry here, fluorine and hydrogen, then the fluorine rips the electron off the hydrogen and says, it's mine. And then they're ions and form an ionic bond. So remember, we had, if the difference in electronegativity is less than 0.4, it's just considered covalent. Between 0.4 and 1.6, it's a polar covalent. More than 2, excuse me. See, 0.4 and 1.6. And then more than 2 difference in electronegativities, then it's going to be ionic. And yes, there was a gap there from 1.6 to 2. Question?
If I were to ask that question of which one has the strongest bond, like tied together, I guess, I mean, there was a question, something like that. Would it be the ionic, or would it be?
Actually, I believe the covalent bonds are stronger than the ionic bonds.
Covalent would be the strongest.
Now, looking at the different bonds and the relative strengths. Now, I have here ionic listed first, but I'm pretty sure covalent is stronger than ionic. These things here are bonds. Well, okay, metals is in this list as well. These here are different. These here are bonds between molecules. Whereas the other 3 are between atoms. Now, metallic, I say, is between atoms. The metallic is actually the entire structure is involved. But these ones in the red there, between molecules, make sure you remember those. An ion, if it comes to a dipole, the dipole has a positive and negative side. If it's a negative ion, the positive side is attracted, and it forms a bond between this ionic molecule and this polar molecule. Dipole is 2 dipoles, like 2 water molecules. Water molecule has a positive side and a negative side. The negative side is where the oxygen is. Well, if I bring 2 water molecules near each other, they're going to rotate so that the negative side from one is attracting the positive side of the other, forming a dipole-dipole bond, which is reasonably strong, which is why water has its special properties. Why water is, well, all of its special properties has an elevated boiling and freezing temperature, right? It freezes at a higher temperature than normally would, and is more dense in the less dense in ice phase, more dense in liquid. Next one is dipole-induced dipole. If you have something with no dipole moment and you bring something with a dipole, the charge will cause a deformation of the charge distribution in the one that doesn't have a dipole moment, giving it an induced dipole moment, and then they bond. Very weak though. So this here is weak. Induced dipole is super weak. That's why we use Teflon coating, because Teflon is a polymer that is a carbon chain with fluorine atoms on it. And those fluorine atoms are going to form very strong bonds with the carbon, and they're going to, because you have the distribution of fluorine all around is going to be a nonpolar chain. And so that nonpolar chain of tightly bound electrons is going to essentially not be susceptible to induced dipole, and thus it does virtually nothing. It just doesn't interact with anything. So we use it as a coating so it doesn't stick to anything. Mixtures, I've already talked about everything on that. Solutions, if you're not part of the solution, you're a part of the, yeah. Solution is a mixture of one chemical with another. We measure concentrations. The one we learned, is the molarity, which was the number of moles per liter. Moles of solute, the thing that's dissolved, per liter of solution. The solution is the solvent and the solute. So that's the molarity. Remember, a mole is the number of molecules. That number for 1 mole is 6.022 times 10 to the 23rd, called Avogadro's number. You do not need to memorize Avogadro's number, but you need to know that a mole is this specific number of molecules. And 1 mole of molecules has a mass in grams equal to the atomic mass. So if you take, for instance, a water molecule. A water molecule has an oxygen, 16, and 2 hydrogens, 1 each. So total molecular mass of 18. If I have 1 mole of water molecule, it will have a mass of 18 grams because of the definition of a mole. Let's not worry about the soaps and detergents. I won't ask that on the test, okay? Chemical reactions, I'm just going to jump to make sure you have these things in your head again. Bad, and Leo the Lion says GER. Bad. Bases accept, acids donate. What are they accepting and donating? Protons. So you can determine if something's an acid or a base based on, is it giving out a proton, which is a hydrogen nucleus, not the electron, but just the hydrogen nucleus, or is it accepting? Leo the Lion says GER is talking about reduction and oxidation reactions. So Leo means lose electrons, oxidation. So if you have something that loses electrons, it was oxidized. GER is gain electrons reduction. If you have something that gains electrons, it was reduced. And those are the 2 types of reactions we talked about, acid-base reactions and reduction, oxidation. We call them redox reactions. pH, I just saw something on Facebook. One of my friends posted how you can use Coca-Cola to do all kinds of cool things like kill insects or clean your tile grout or clean your toilet bowl. Why can it do all of these things? Because its phosphoric acid is very strong. It has a pH of 2.5. Low pHs mean acidic. 7 is neutral. High pHs mean basic. Now, vinegar, white vinegar, 5% white vinegar is just about the same acidity. It's acetic acid rather than phosphoric acid, so it's slightly different in its action, but I would go ahead and use vinegar for my cleaning and bug killing rather than Coke. Cheaper. Good question?
I was just going to say, is that why when we drink Coca-Cola, well, at least for me, I feel like it kind of burns a little bit?
Mm-hmm. Same thing if you eat pineapple, right? That's also highly acidic, right? Some people get all bent out of shape. Oh, how can I eat this thing that's so acidic? Well, a lot of things we eat are quite acidic. It's not in and of itself something that says you shouldn't eat it. Although, it's probably better not to. All right. Have a great day. I'm sorry I only got halfway through chemistry. I will see you. When is the exam? Monday. Monday at 10 a.m. Here. Question?
Since it says that the test is a lot of the astronomy you just did, what should we be studying for that?
For the astronomy, okay, so we only covered astronomy, the solar system. That's basically all we covered, right? So make sure you know the planets in order. the properties of the planets, like which ones have atmospheres, which ones have moons, which ones have odd rotation. Why do we have eclipses? Why do we have phases? Those kinds of things are what we'll be looking at with astronomy.
Okay, so strictly what we went over like in lecture.
Yes, strictly what we went over in lecture.
What about the other stuff, the eras,
Like science.
yeah.
I didn't get to it, but I have my review stuff here for it.
I didn't get access to it, so I tried logging into the OneNote.
I can't log in.
It won't let me log in.
Yeah.
No, it won't let me. So I've been using your YouTube lectures.
I don't know what to say.
Is there any way there can be a screenshot and
Or-
post it?
Yeah, I can take this and post it to Moodle.